Welcome back. In this unit, we'll talk about virtual memory. Let's first talk about virtual address. The kernel provides a separate virtual memory for each process. The virtual memory of a process holds code, data, and stack for program that is currently running in that process. Running applications see only virtual addresses. For example, program counter and stack pointer store virtual addresses. Pointers are virtual addresses. Jump and branch instructions refer to virtual addresses. The advantage of maintaining a separate virtual memory for each process is that each process is isolated in its own virtual memory. As a result, processes don't interfere with each other. When process tries to load or store to an address, the data is loaded from or stored to a physical address. However, because running application sees only virtual addresses need to be translated to physical addresses. The address translation is performed by a hardware unit called MMU. Memory Management Unit. In this unit, we're going to introduce 5 address translation approaches. The simplest address translation approach is called dynamic relocation. Dynamic relocation is performed in hardware by MMU with 2 special registers, relocation register and limit register. For simplicity, we'll refer to the value stored in the relocation register as R and the value stored in the limit register as L. The running process's virtual memory is a contiguous chunk of physical memory. Relocation register stores the physical offset of the running process's virtual memory. Limit register stores the size of the running process's virtual memory. Because there are more than one processes, each with its own virtual memory, the kernel must maintain a separate pair of R and L values for each process. When switches process, the kernel is responsible for placing the R and L values in the relocation register and the limit register respectively. Bqp translation is done as the following. If the virtual address is larger than the range of the virtual memory, that is, V is greater than or equal to L, then it cannot be fed into the virtual memory. This results in exception. Otherwise, P simply equals to V plus R. What are kernel's responsibilities then? As you can see from this diagram, the kernel needs to map virtual memory to a contiguous chunk of physical memory and keep track of which parts of the physical memory is free and which parts of the physical memory is in use. This usage information is useful when kernel needs to allocate or free variable sized of contiguous chunks of physical memory. The advantage of dynamic relocation is that it is very simple to implement. On the other hand, it leads to external fragmentation. External fragmentation means that there are unused blocks in the physical memory between the allocated blocks. We want to avoid external fragmentation as it leaves holes and wastes physical memory. The solution to external fragmentation is paging. Paging is performed in hardware by MMU. Physical memory are divided into fixed-sized chunks called frames. Virtual memory are divided into fixed-sized chunks called pages. Each page is mapped to a frame. Each process has its own page table for lookups. The address of the page table is placed in a special register in MMU called Page Table Base Register. For simplicity, we'll refer to the value stored in the Page Table Base Register as PT. Because there are more than one processes, each with its own virtual memory and its own page table, the kernel must update the page table that the page table base register points to with switches processes. Each page table entry contains a page number and a frame number that the page number is mapped to and a valid bit that indicates whether the entry is valid or not. It also keeps track of all other useful information. Each page table entry may contain extra fields such as a write protection bit, a reference bit, and a dirty bit. If the write protection bit of the page is set by the kernel, this page is read-only. Any attempts to modify it will result in exception. The reference or use bit is set by the MMU to indicate whether the page is recently used. Similar to the reference bit, the dirty bit is set by the MMU to indicate whether the page is recently modified. In this example, page 0x0 is mapped to 0xFF. It is read-only, not recently used, and not recently modified. Since the second entry is not valid, its write protection bit, reference bit, and dirty bit are not set. And in the last entry, page 0x2 is mapped to frame 0x1e. It is writable, recently used, and recently modified. Now, let's look at how address translation is performed. The virtual address is divided into two parts. The upper n bits is for page number, and the lower n bits is for offset. The page table lookup is the same as the normal map lookup. After the page table entry PTE is found, we'll check the valid bit and raise this exception if the page table entry is not valid. If the page table entry is valid, the frame number is prepended to the offset to produce the physical address. As we can see from the diagram, there are 2 to the power of m entries in the page table, so the size of the page table is the number of entries, that is 2 to the power of m times the size of each page table entry. Recall the definition of paging. The virtual memory is divided into fixed-size chunks called pages. Therefore, the number of pages is the size of the virtual memory divided by the size of each page. The advantage of paging compared to dynamic relocation is that it solves external fragmentation. It does, however, has two disadvantages: performance overhead and internal fragmentation. Next, we'll focus on reducing performance overhead. Page table lookup introduces extra memory operation. To reduce page table lookups, we introduce a small, fast, dedicated cache that only stores page table entries. This cache is called TLB, shorthand for Translation Look-Ahead Buffer. We need to incorporate the changes introduced by adding TLB into the kernel. Recall that each process has its own page table. However, there is only one TLB for all the processes. We don't want one process to mistakenly use the page table entries of another process that is stored in the TLB when process switches. Therefore, the kernel is responsible for clearing the TLB when it switches processes. There are two kinds of TLBs: hardware-managed TLB and software-managed TLB. Let's first look at hardware-managed TLB. MMU must understand kernel's page table format and handle TLB misses. If the page table entry is found in TLB, in other words, TLB hit, we simply return the mapping. Otherwise, there is TLB miss. MMU will find the page's frame number in the page table and add this mapping to the TLB. If TLB is full, it will randomly evict one of its entries and store the mapping. Then it will return the frame number. For software-managed TLB, if the page table entry is found in TLB, in other words, TLB hit, we simply return the mapping. Otherwise, there's TLB miss, and TLB miss exception is generated. The kernel must handle the TLB miss exception by performing page table lookup and adding the mapping to the TLB, evicting one entry if TLB is full. After the TLB miss is handled, the instruction that caused the TLB miss is retried. Since most of the recently used page table entries can be found in TLB, and page table lookup is only performed when TLB miss, this greatly reduces the number of memory operations. Now, we have already discussed the solution to performance overhead problem of paging. Now, let's look at how to resolve internal fragmentation problem. First of all, let's understand what is internal fragmentation. Internal fragmentation is the wasted space within an allocated block of memory. Virtual memories are large. For example, MIPS virtual memory uses 32-bit virtual address, so its size is 2 to the power of 32 bytes, 4 gigabytes. x86-64 uses 64-bit virtual address, so its size is 2 to the power of 64 bytes, 256 terabytes. Now, Let's consider a small quicksort program that sorts an array of integers of size 1.2 megabytes. This program will take only 1.2 megabytes of 4 gigabytes virtual memory. The data segment and the stack segment are widely separated for the stack to grow, so there is a wide gap between the data segment and the stack segment, and as a result, most of the virtual memory is unused. So how well do dynamic relocation and paging handle large but sparse virtual memory? Dynamic relocation will allocate a large contiguous chunk of physical memory, and most portion of the chunk is not used, so we have a set phase here. What about paging? A large page table will be created where most of its entries are marked as invalid. This large page table takes up a large contiguous chunk of kernel memory, so we have a set phase here too. Next, we will examine two solutions to internal fragmentation. One way to solve internal fragmentation is segmentation. We divide the virtual memory of a process into 3 segments: code, data, and stack. Then we maintain separate mappings for each segment into the physical memory. In other words, the code, data, and stack segments do not have to be contiguous. MMU manages 3 pairs of limit and relocation registers, 1 pair for each segment. Since each process has its own virtual memory, the kernel must maintain separate sets of relocation offsets and limits for each process, and it is responsible for placing them in MMU registers when process switches. The virtual address is divided into 2 parts. The upper n bit is used for segment number, and the lower n bit is used for offset. L_segment number is the limit register of the segment. R_segment number is the relocation register of the segment. The translation is the same as the dynamic relocation translation. If the virtual address is larger than the range of that segment, then it cannot be fit into the segment. This results in exception. Otherwise, P simply equals to R_segment number plus offset. Another way to solve internal fragmentation is multi-level paging. We split the single-level page table into multiple small page tables and add page table directory for each additional level. For simplicity, we refer to the page table directory as PTD. Without the loss of generality, we will consider 2-level paging. The virtual address is divided into 3 parts. The upper n bit is used to index into page table directory to find the right second level page table. The next n bits is used as page number to index into the page table to find the frame number. And the lower k bits is used for the offset. The first lookup in the page table directory is to find the right page table. If the page table directory is not valid, raise exception. The second lookup and the translation is the same as the single level paging we discussed earlier. If the second level page table directory is still too large, we can introduce additional levels of page table directories such that each level only takes up a small contiguous chunk of kernel memory. One drawback of multi-level paging is that as the levels of paging increases, the cost to handle TLB miss also increases. In single-level paging, only one lookup is required to handle TLB miss. For two-level paging, two lookups, one on the page table directory and one on the page table, are required for TLB miss. If we have n-level paging for a very large virtual memory, n lookups are required for TLB miss, and the TLB misses become expensive. By the end of this video, you are expected to know what is virtual memory and the idea behind it, dynamic relocation and its pros and cons, paging and its pros and cons, TLB and why it is added, segmentation, what problem does it solve, multi-level paging, what problem does it solve, the cost of TLB miss.